All right, the topic now is optics. But optics is really the study of electromagnetic waves. Those are waves that consist of both electrical fields and magnetic fields oscillating. So you'll hear me use these terms. Electromagnetic waves, you know that maybe as light or electromagnetic radiation, or maybe simply as radiation. All of those terms right there are interchangeable. Most people, when they talk about light, they're really talking about the visible part of the electromagnetic spectrum, but any part of the electromagnetic spectrum could potentially be called light. For example, you could have radio light, or X-ray light, or visible light, or infrared light. All of those represent different wavelengths of electromagnetic waves. And really the only difference between all of the parts of the electromagnetic spectrum are things that we call wavelength, lambda, which we'll symbolize as lambda here. That stands for wave length. And the actual unit of that is really a unit of length, so meters. And frequency. Which has a unit of inverse seconds, which you know we have called a hertz. Okay, now those are the only real differences between any region of the electromagnetic spectrum. And there's a relationship between these two things and the speed of light. The speed of light, which we'll symbolize as c here, is specifically the speed of light in a vacuum. And we will almost entirely assume that light is traveling in a vacuum. Now this is a very well-known number. It turns out to be 299799245 meters per second. Okay, now that's an odd number to remember. We're just going to remember it this way: 3 times 10 to the 8th meters per second. And that's the speed of light. Now the relationship between all three of these quantities we would call the wave equation. And it works this way. Wavelength is equal to the speed of the wave divided by the frequency. Now it also turns out that each of these waves, what we call waves, could be considered an individual particle. And when an individual particle of light, a quantum of light, is described, the word that's used is photon. So a photon of light is the smallest amount of light that you can have. Now a photon of light has an energy associated with it. You may have heard in the past talking about the wave-particle nature of light, or the wave-particle duality of light. That's because sometimes, depending upon how you look at light, it behaves like a wave. Other times it behaves like a particle. So the photon is a particle of light. And that particle has a certain energy associated with it. And the energy, let's symbolize that as E, the energy of a photon of light is equal to h times the frequency. The h here is called Planck's constant. And you can look that up in the textbook. Let's talk about the electromagnetic spectrum. You're probably familiar with visible light. Visible light consists of all of the colors of the rainbow. So within this narrow region of the electromagnetic spectrum, we have red, orange, yellow, green, blue, indigo, and violet. So those are the colors that we typically name. Now every color is a mixture of some of those, but these are the colors of light. The wavelength range for visible light very approximately goes from 700 nanometers to about 400 nanometers. Okay, so that's the range of visible light. Now, the electromagnetic spectrum does not stop here. It goes on. For example, past the infrared, past the red over here, there is the beyond the red part of the spectrum, and that is called the infra. Well, the infrared has longer wavelengths, and you can tell the wavelengths get longer as you go to the left here. So these would have a longer wavelength and also a lower frequency, because the wavelength is inversely proportional to the frequency. And also energy, which is related to h times the frequency. As the frequency decreases, the energy also decreases. So going to the left here, from visible into infrared, we're going into the region of longer wavelength, lower frequency, and lower energy. Okay, beyond the infrared, there's a region that is often called the microwave region. And a lot of communications happens in the microwave region. Beyond the microwave region, there is the radio region. So radio wavelengths fall into this category. And you're familiar probably with most of these wavelength regions of the electromagnetic spectrum. Radio is used mainly for communications, so your cell phone uses radio. You listen to radio stations, television stations, satellite broadcasts come through in the radio region. On the other side of the visible spectrum, we have beyond the violet, that is the ultraviolet, which is, we just call UV. Now, UV radiation is the kind that gives you sunburn. It's the kind that can cause skin cancer. And as we go farther to the right here, you'll notice that we're getting into shorter wavelengths, which means higher frequency, which also means higher energy. So these higher energy waves are typically more dangerous the farther we go to the right-hand side. Okay, after the UV region comes the X-ray region, and you're familiar with X-rays if you've ever been to a dentist and they've X-rayed your teeth, or you've broken a bone and they've X-rayed that. X-rays have the property that they can pass through the soft tissue of your skin, but the hard tissue inside blocks the X-ray, so that's why you can see inside. Inside your body. It's used as a medical diagnostic tool. Nevertheless, it is dangerous. So if you're a woman, regardless of how old you are, they always ask you, are you pregnant? Because X-rays could potentially damage a forming fetus, and they need to know that. Okay, also you don't want to be exposed to too many X-rays. Okay, beyond the X-ray region, there is the gamma ray region, or gamma rays. Okay, the gamma ray regions are very high energy radiation, very short wavelength, very high frequency, and anything that goes beyond that is still considered gamma rays. Okay, just like anything beyond radio is still considered radio waves. And the only difference between all of these regions of the electromagnetic spectrum, like I said, are the wavelength, frequency, and energy. So this down here represents long wavelength region, therefore low frequency region and low energy region. Whereas the opposite end of the spectrum, these are the short wavelength in, high frequency and energy end of the electromagnetic spectrum. So these are all forms of electromagnetic waves, all different forms of light that travel at the same speed in a vacuum, and that is this speed c, 3 times 10 to the 8th meters per second. And that is, like I said, a very well determined number, has been determined experimentally. Now, there are a few things that you need to know about electromagnetic radiation. First of all, I've already said that it consists of electric and magnetic fields that oscillate. Now, they oscillate in phase. So when I say they oscillate in phase, you have to keep in mind that the electric field and the magnetic field are always going to be perpendicular to each other. They are always at right angles to each other. So if I drew an electric field, let's say this represents an electric field in that direction, and this electric field has the ability to oscillate, meaning that its magnitude grows and then its magnitude shrinks. Okay, and we could even say its magnitude grows in the opposite direction and then its magnitude shrinks. So we've got a center point here about which that electric field would oscillate back and forth and back and forth. Well, the magnetic field would oscillate at 90-degree angle to that. So there's the magnetic field, and it would oscillate this side as well. So these are always at right angles to each other, and they are always in phase with each other. Now, light itself is considered a wave. It's a transverse wave. The direction of the velocity is always perpendicular to the vibration, or in other words, the oscillation. Now, what does that mean? I told you that the electric field and the magnetic field are always perpendicular to each other. Well, both of those are always perpendicular to the direction of travel. So we're talking 3 dimensions here. The direction of travel then is going to be, in this case, out of the board. So let's draw that a different way then. Let's say that we have a photon that is traveling in this direction with a velocity v. Well, the electric field could be in that direction. The magnetic field, though, is going to be out of the plane of the paper. Now, you can always tell the direction of travel by a cross product. In other words, E cross B tells you the direction of travel. So in this case, E points up, cross your hands into B, your thumb points in the direction of the propagation of energy or the direction of travel. So if that's a photon, it's carrying energy from this point to some point to the right. So that's what I mean, the direction of travel. Now, E and B are always perpendicular. The E field is always perpendicular to B, and E cross B gives you the direction of travel. Now, both E and B fields vary, and they vary sinusoidally. And that is that sinusoidal oscillation of the fields that induces, via Faraday's law and via Maxwell's law, a perpendicular other field. All right, that means that we can write equations for the electric field and the magnetic field, and those equations look like this. E equals some magnitude, that's the amplitude of the sinusoidal oscillation, times the sine of some angle. Now, this angle is going to look different than things we've seen before. It is going to have an omega t in it. But if you'll think about, previously we had an omega t for our sinusoidal oscillation of something like a voltage source. Well, that voltage source was not moving through space. So these waves vary over time. Yes, they do, but they also vary over space. So a transverse wave then could look something like this, but rather than it just setting still and oscillating like that, it is actually moving in some direction with a velocity v. So we have to account for this movement along, we could call this the x-axis here. And when we do that, I'm not going to derive this for you, there's no need to, but what goes inside here is k times x minus omega t. Okay, now the omega you recognize, that is the angular frequency. Omega is 2 pi times the standard frequency. But k is something new here, and this is called the wave number. Specifically, the way that we're going to treat it, it is an angular wave number, just like this is an angular frequency. This is an angular wave number, and it is defined this way as 2 pi over lambda. Okay, now that takes care of the fact that we have a wave that not only oscillates but also moves here. That's the form of the electric field equation. The magnetic field equation is going to look exactly the same way. It has some B sub m times the sine of kx minus omega t. Now we don't have to include a dash or plus phi. We don't include a phase angle, because these two waves are always going to be in phase with each other. They're always going to be perpendicular to each other. Okay, so these are the equations then that describe an electromagnetic wave. Now, interesting thing to notice here. Just notice this at this stage. If I take omega and divide by k, this is going to be what? 2 pi f divided by 2 pi over lambda. That turns out to be then, when I cancel the 2 pi's, bring the lambda up top. That's just going to be the frequency times the wavelength, which is c, the speed of light, from the wave equation. Just notice that, and we may return to that in a minute. Now, I said that the electric fields and the magnetic fields are always perpendicular to each other, so it's kind of hard to draw. Nevertheless, I'm going to try to here. Let's say that we have an oscillating field that looks something like that. Now, I'm drawing this at kind of an angle because I want this to represent the direction of travel here. So this is oscillating perpendicular, let's say vertically like this. I'll draw those lines to indicate that's the direction of oscillation here. And this could be the E field. Well, then the B field is going to be perpendicular to that. And remember, E cross B gives you the direction of travel. So if this is the E field here, then at the same time that is in that position, this is in this position at a right angle to that. And then over here, E cross B still gives that, and then this comes back around like that, and then that goes around like that, and then this comes around like this. See, it's kind of hard to draw. But the point here is I want you to see that we've got B fields oscillating in one plane, E fields oscillating in the other plane, and then it's propagating along in this direction. So the best model that we have to explain the way light propagates and moves and creates itself is a self-propagation model like this. So these two fields essentially create each other, and that creation then propagates the energy along. Okay, that's the best model we have to explain light, and light still to some degree remains a big mystery. Now, the textbook at this point goes into a lot of mathematics, and one of the ways that it sets up the mathematics is it creates a x, y, and z coordinate system here. And then what it does is it holds E constant in time and B constant in x. Remember, the equations for E looks like that. But we've got two variables here. X varies with time, x changes and time changes. So those are two variables there that are related, but nevertheless we have two variables in this case. And to plot it on a graph like this would require that we have a four-dimensional graph that could also include time. All right. But the way that the textbook does this is it freezes one of these in one of those variables and the other one in the other variable. And what it does is it holds the E constant in t and the B constant in x. And it allows the two to change in the other variable. Now, it goes through a lot of trouble here. It goes through a lot of mathematics, and I want you to look at that in your textbook. Understand what's happening here is the electric field oscillating in one direction is generating a magnetic field in the other direction. So those two things are very much related. But in the end, here's what happens. We're skipping a lot here. In the end, it is discovered that c, that's the speed of light in the vacuum, is equal to 1 over the square root of mu naught epsilon naught. So remember these knots here, that indicates, we called that the permeability of free space and the permittivity of free space. Okay, but this gives the speed of light in free space, which is just another word for vacuum. So if you take the value for mu naught and you take the value for epsilon naught and you plug them in, you get a number that is very, very close to that speed of light. the reason that it might be off would be because of rounding errors and not using perfect values for mu naught and epsilon naught. But this is what the mathematics of all of that section of the textbook boils down to, that we discover that the speed of light can be determined from those fundamental quantities. And that also means the speed of light depends only upon the material that the electromagnetic wave is passing through. It does not depend upon wavelength. You notice there's no wavelength here, there's no frequency here, there's no energy here. It's just this right here, mu naught, epsilon naught. And if we were to change the material, the mu and the epsilon would change, meaning that the speed of light would change. As it is shown now, this is for a vacuum. So the speed of light is constant then. Velocity depends upon the medium, not on the wavelength or anything else. So now we're going to shift gears and we're going to start talking about various characteristics of light. The first one we're going to talk about is intensity. The intensity of light is, if we think in terms of visible light, it's how bright something appears. How much energy are you measuring from a radiation source like that? So we'll talk about intensity. Then we'll go on and we'll talk about polarization. Polarization has to do with the electric and magnetic fields becoming lined up, because not every light source emits electric field waves in the same direction. So the one wave may come off in this direction, the next come off in that direction, the next come off in this direction. So over time, those E field directions are everywhere. It's all over the map. Polarization is a way to take those E fields and line them all up. So we'll talk a little bit about that. And then we'll talk about two more characteristics. We'll talk about reflection and refraction. And these two things are naturally going to lead into discussions of mirrors and lenses. Okay, that's where we're heading. When it comes to intensity, I'm losing my pen here. When it comes to intensity, intensity, which we'll symbolize as big I, falls off as 1 over the distance squared. You can think of intensity as how bright something appears, but intensity could also be a true measure of how much energy something is emitting into space. However, the amount you measure is the intensity. And intensity falls off as 1 over distance squared. So let's say that we have something that is emitting light, and it's a perfect emitter, and it's emitting light outwards in all directions. A real-life example of this might be something like a star. Okay, and that star has a certain amount of energy that it's emitting outward into space, and if I'm out here a distance, let's call that distance r1 away, then all of the energy that this thing is emitting from its surface is now spread out over this sphere. In other words, what was here on the surface has now been spread out over all of this region here. So the energy per area is, well, let's say it's the total energy E divided by 4 pi r1 squared. And that we'll call the initial intensity at a distance of r1. Now let's go out to twice that distance out here. Let's go another r1 away, so now we're at 2r1. Now what is the energy per area? Well, it's still going to be E divided by 4 pi r1, but we're 2r1 squared. Okay, we can take this and we can kind of factor it out. I'm going to draw a line so you don't think this is a continuation of that. This is E on top. We've got 4 pi r1 squared and a 1/4 out front if I take this 2 here and factor it out front. So what's in the parenthesis here is I naught. So the new intensity at a distance twice as far away is going to be 1/4 of what it was initially, right here. So that shows that the intensity of light falls off as 1 over distance squared. So if I made a graph here, of distance and intensity, then at a distance of 1, the intensity would be 1. But at a distance of 2, the intensity would be 1/4 of what it was originally. At a distance of 3, the intensity is going to be 1 over 3 squared, or 1/9. And at a distance 4, it's going to be 1 over 16, and so forth. So that's the nature of light. It falls off as 1 over distance squared. Okay, that's really all we can say about intensity. Let's go on now and talk about polarization. Okay, when it comes to measuring the waves, the oscillation of the waves of electromagnetic waves, typically the electric field is usually more measurable, more easily measured than the magnetic field. And so whenever we talk about polarization, we're going to talk about the E field vector of an electromagnetic wave. And we'll define a plane of oscillation. So let's say this represents the direction of travel. So a photon, a ray of light is coming out of the page here. Then E would be in that direction and in that direction. So we've defined this direction of oscillation, this plane of oscillation for the electromagnetic wave. Now, signals that are broadcast for, say, a TV transmitter antenna, they have all their E vectors lined up in a plane, okay? That's called plane polarized. So they have everything going up and down, all right? But a normal light source does not produce light that is all lined up. In other words, a normal light source does not produce polarized light. So if I had something like light coming from the sun, for example, let's say this represents again the direction of travel coming straight out of the page, then the E field may be here and here, oscillate in that direction for one oscillation, but in this direction for another, in this direction for another, in this direction for another, and I'm just drawing them in every possible direction here. And the point here is it's definitely unpolarized, while this over here would be polarized. Okay? Now, a Polaroid. A Polaroid is a substance that transforms unpolarized light into polarized light. The classical model for a Polaroid is called the picket fence model. And the basic idea is that a Polaroid consists of long molecules embedded in plastic, and the molecules are lined up in parallel lines. So if I were to draw, let's say, a plastic film, like a filter, light's going to pass through that. Then the molecules in this would be lined up in such a way that they would all line up like that. Okay, now light, if you think about it being unpolarized like this, coming towards a thing like this, all of those unpolarized rays that are coming in every direction would not be able to pass through the picket fence. So think of this as having gaps, and only the electric waves, the electric field waves that are in line with these gaps will be able to pass through. So it's like a picket fence. Not everything can pass through. Only if you go through the slots are you able to get through. Now, that's a classical way of understanding light. The truth is a little more complicated than that. But nevertheless, if you have this kind of light going in to a Polaroid filter, then this kind of light will come out of the Polaroid filter. So if you say we have light, let's draw it as coming in from the backside here, and that light has some intensity, we'll say I naught, then when it comes out of the filter here, it's going to have a different intensity I. Now, if I naught is unpolarized, then I will be polarized. But because you've knocked off some of the electric fields that could not get through the picket fence, then the intensity of the polarized light is going to be less than the intensity of the unpolarized light that was the incident light. So the incident light has a greater intensity than the light that has passed through, the polarized light. Now it turns out that the intensity of the light that comes through is 1/2 of what the initial intensity was. I think you might see a little bit later why that's the case, but that is indeed the case. And it holds if the incident light is unpolarized with randomly oriented electric vectors, E vectors, that passes through the filter. But what if we take now this polarized light and we pass it through another filter? And maybe this filter is at a different angle here. Okay, well, what's going to happen? Now, you might think, well, when the light comes out of this first filter, it's all lined up this way, straight up and down. So when it hits this, none of it's going to be able to pass through because none of it lines up with this. If that's the case, that you're thinking that, well, then you're thinking wrong. You're thinking in terms of classical physics, that these things are real objects that go up and down. But this is just our model of light. The truth is, if we think of an E vector going in that direction, you could break that up into components with one going this way and one going that way, with some angle between. We could call that angle theta. And then if that's the case, this angle here is going to be the E cosine theta component. This would be the E sine theta component. And look, it's going to be the cosine component that's able to go through. So these E vectors, when we line them up like that, that's just our way of our understanding light. Remember, light to some degree is still a mystery. So this just represents a vector that can be broken up into a component that is parallel with these lines and a component that is perpendicular to these lines, whereas the E cosine theta component are going to be the ones that go through. Okay, if that's the case then, now going back to this just for a second here, I need to say one other thing about this intensity here. The intensity, which we'll call I naught, is related to the electric field. And specifically it's related this way, 1 over C mu naught times E squared. Once again, that is something that has fallen out of the mathematics that we've skipped, but that is indeed the case. Now, let's use that information to talk about Polaroids one more time. So let's suppose that we have a Polaroid lined up this way. We have some initial intensity going in, I naught, 1 over C mu naught E squared. Now you have seen that if we have an E vector going in that direction, then the E that lines up with this, if that's the angle theta right there, then the E that lines up with this is the E cosine theta, and that's the portion that passes through the filter, through the Polaroid. So E, Y, let's call that, is equal to E times cosine of theta. Okay, if we take this E and we plug it in here, then a new intensity is going to be 1 over C mu naught times E cosine theta squared. So this is going to be 1 over C mu naught E squared times cosine theta squared. Now, what's here is actually I naught, so I equals I naught times cosine squared of theta. Now, this is the one that I want you to know. For already polarized incident light, then the intensity after it passes through the polarizer is given by this equation right here. So I naught here would represent the intensity of the light that is incident upon this. If we assume that the incident light is random E vectors in every direction, then what happens is this whole thing right here, you average over all possible values of theta, and it turns out that the intensity that passes through, assuming the incident is randomly distributed E vectors, is going to be 1/2 of what it was initially. So that's where that 1/2 comes from when you pass unpolarized light through the first filter. But if you pass if you pass polarized light through another filter, then you use this equation here. Okay, and this comes about because the average of cosine squared is going to be 1/2. All right, let's use this information then to work a problem. Let's say we have light that is traveling along this axis here. We could say that's X, that's Y, and this would be Z or whatever. Okay, and light is traveling along that axis, and let's place a Polaroid filter right here on that axis. And let's say the angle relative to a straight up and down line here, relative to, let's say, the y-axis, is at that angle right there. Let's call that theta 1. And unpolarized light is coming into that first filter. And then let's put another filter out here, like that. And let's say that this one has an angle as well, relative to the y-axis. And this angle here, from there to there, is going to be theta 2. And now let's put a third one down here, and let's turn it back this way. And once again, this angle here is theta 3. Now let's give ourselves some angles values here. That'll theta 1, let's make that 40 degrees. Theta 2, let's make that 20 degrees, but notice it's measured from the bottom here. It's not measured from the top, so it's 20 degrees. And then theta 3, well, we can just make that 40 degrees again. Okay, now the question is, when it goes in here, it has some intensity, I naught. But when it comes through the first one, it's going to have some intensity I1, some intensity I2 when it passes through the second one, and then some intensity I3 when it comes out of the third one. The question is, what is the ratio I3 over I naught? Okay, what is that equal to? Okay, we can figure this out. First of all, if it's unpolarized light going in, when it passes through this first one, then I1 is going to be 1/2 I naught. And then when it goes through the second one, then I2 is going to be I1, that's the incident intensity, times the cosine squared of the theta. But what is the theta? You got to understand what this angle is. This is the angle between 1 and 2. So this is the angle between these two things here, okay? And if we plug in for I1, then this becomes 1/2 I naught cosine squared of the angle between 1 and 2. All right, now I3 is going to be I2, that's the incident intensity, times cosine squared of theta, but theta is going to be the angle between 2 and 3, so let's just call that 2, 3. Now if I plug in for I2, then this becomes 1/2 I naught cosine squared of theta 1, 2 times cosine squared of theta 2, 3, like that. All right, so if I take this relationship here, there's I3, there's I naught, and I solve for I3 over I naught, which is what we want, then that's going to be 1/2 cosine squared of theta 1, 2 and cosine squared of theta 2, 3. All right, now we need to figure out what these angles are here. So here's the way I'm going to do it. Let's say this is cosine squared of this angle between 2 and 1. Now, in terms of all of those angles right there, you can notice this. Notice that if I take theta 1 and I add the angle between the two, theta 1, 2, and then I add theta 2, that all of those have to equal 180 degrees. All right, so what does that mean? That means theta 1, 2 is going to be 180 minus theta 1 minus theta 2. So this theta 1, 2 then is 180 minus theta 1 minus theta 2. And then cosine squared is going to be, this is 2, 3 here. We do the same sort of thing. It ends up being 180 minus theta 2 minus theta 3, like that. All right, we've got values for theta 1, theta 2, theta 3. We should be able to plug those in. And when you plug those in, you end up with 0.03125, meaning that I3 over I naught is about 3.1%. So the intensity of what comes out of the 3 end is about 3% of what went in on the original end. So the intensity has been dramatically reduced by passing it through these filters. But when it comes out here, it's going to be polarized in that direction of those lines in the polarizer there. Okay, so there's a type of problem that you may see soon. Okay, now what's left is reflection and refraction. So we'll talk about reflection and refraction in the next videos. It's not hard.